Thank you very much. I'm John Donners. I work for Atos. I will present the first part of the presentation. We'll tell something about the CPU that's being used in Levante. One slide about the cluster, especially the switches and what you can you yourself configure about it. Then quite some slides about the compiler and what new is there relative to Mistral. Then a few things about OpenMP and MPI, how you can best set your runtime environment for your applications, some Slurm examples, and then three known issues, which one is solved and two are still in progress. Four known issues. Sorry, I think I only have three in here, but we'll come to that. Okay, about the CPU. This is a nice picture of the CPU. And most interesting is that the actual cores of the CPU are in these small black triangles here, not in the big one. And every one of these small black squares has 8 cores in them. So in total, there's 64 cores on this CPU. Here you see a schematic of such a CPU, and here it's in this schematic. There's only 32 cores, but and you see it's only half full. Every one of these 8 boxes. Here you see 4 cores. Each one has a L2 cache, a private L2 cache, and these 4 cores, in this case, 4 cores share one L3 cache of 32 megabytes. In a CPU that is built in Levante, there's 8 cores in such a small box. So 8 cores share one L3 cache, and you will see that number coming back later when we talk about the optimal number of OpenMP threads. Then there is here lots of memory channels around, and I will come to that in the next picture. Not yet this one. Here you see there's still a difference between. So what is built in Levante is this CPU, this Milan CPU on the right. You see here there's 8 cores. Which share one L3 cache of 32 megabytes. In the previous generation from AMD, which was called Rome, there were 2 L3 caches, and there the L3 cache was only shared by 4 cores. So that is the main difference between the Rome and the Milan CPU. Yes, maybe to present the difference with the Intel CPU that was built in Mistral is that here this L3 cache is only shared by 8 cores, while the whole CPU has 64 cores, whereas on Mistral the L3 cache was shared by all the cores in the CPU. So that is one of the differences between this CPU and the CPU in the previous system. Here is again another picture of the same thing. You don't have to read everything. This is a picture that you could generate yourself on the nodes as well. That's the hwlocks command. It can plot these graphs. It will analyze the hardware on the system. What you will see here, this large graph. I hope you see my mouse cursor as well. This is one CPU. And this one CPU is divided into 4 pieces, 4 NUMA nodes. This is also one of the big differences with the Intel CPU on Mistral, which had the CPU only had 1 NUMA node. So within a CPU there was no NUMA. All the cores had the same latency and bandwidth to all the memory. In this case, that is different. There's 4 NUMA nodes. So every NUMA node then has 16 cores that have the best bandwidth to the memory on their local memory and have a slightly higher latency to the 3 other NUMA nodes. So every NUMA node has 2 of these small black boxes with each 8 cores and 1 L3 cache. So what you already hear is that the memory hierarchy is much deeper on Levante than it was on Mistral. Here you have 8 cores sharing 1 L3, then there's 16 cores sharing 1 NUMA node, and there's 4 NUMA nodes on 1 CPU. And then there's the same thing again on the other CPU. On Levante, you had all the cores shared 1 L3, and all the cores on a CPU had, on Mistral had 1 NUMA node. So you see that the memory hierarchy is much deeper. Here you see again what I talked about, that there's 4 NUMA nodes on 1 CPU. There's 2 CPUs on a node, so there's 8 NUMA nodes in total on each node. That's what you see here. You see nodes 0 until 7, and on the vertical axis the same thing. What you see is this is a measure for the latency when you want to access memory on a different NUMA node. So your core that you're close to NUMA node 0. If you want to access NUMA node 4, then the distance is 32. So it indicates it will take much longer to get memory from there than it takes from your own NUMA node. Take the numbers with a grain of salt. That's an estimate on of how large the latency is. So the lowest is on your own NUMA node. It's a bit larger on a NUMA node within your CPU, and it's a lot larger on a NUMA node of a different CPU. This output you can also see in the nodes yourself with this command, NUMA control -h. If you can log in on the compute nodes while your job is running, one of the commands which you can do to see if your program is running correctly is the hstop command. And what you then see is all the logical CPUs on your on the compute node and how busy they are. So what you see here is 4 columns, and every column has 64 logical CPUs. So here it's from 0 until 34 only displayed, but if you make the font a bit smaller, you will actually see 0 until 63, 64 until 128, and so on. Now here this is, you'll notice there's 256 logical CPUs, but there's only 128 physical cores on a node in Levante. So every physical core has 2 hyperthreads.
Well, they call it SMT.
SMT, okay, sorry. The important thing to remember is this first column, so the first 64 logical cores is the first, the 64 core, first 64 cores of the first CPU. These are the 64 cores of the second CPU, and these are then the SMT threads of the, so 128 until 191 are the SMT threads of the first CPU again, and these are then the SMT threads of the second CPU. So in this case, you see the program seems to be running nicely on the first thread of all the cores. So that looks this looks fine to me. Something about the frequencies and other things. So the nominal frequency of the CPU is 2.45 gigahertz. So this is the frequency that it can always achieve for your application. And the idea is that the turbo frequency allows the CPU to go to a higher frequency if there's still enough energy available. So what that means is that as long as the CPU does not run too hot and it's not already using a lot of energy, it's maybe the application's waiting quite a large part of the time for memory, then a core could go up to 3.5 gigahertz. The memory bandwidth to the memory is 350 gigabytes per second. To achieve that, you would need to use at least 32 threads, which are all using all the different NUMA nodes, and then you can achieve this kind of memory bandwidth. The bandwidth between the CPUs, so if you need to get memory from a NUMA node that's not on your own CPU, that's 188 gigabytes per second. And I think this is bidirectional. So this means if you both go from one CPU to the other, you read, and at the same time you do the same thing the other way around. Yes, for SMT, it can give an improvement, but it depends a lot on your application. For me, I think it's usually the proof of the pudding is in the eating. You just try it out and see if that actually gives an improvement for your application. Maybe Harald wants to.
No.
Good. And usually for OpenMP, that's interesting to try. For MPI, it usually does not give an improvement. Okay, that was about the CPU. I don't know if there were any questions. Otherwise, I will just continue with one slide about the cluster. What the cluster has is 3 levels of switches to connect all the nodes in the system. And you have some control over how you want your jobs to be laid out on the system. So Slurm will always try to put your job as as close as possible together. It's up to 48 nodes. It's possible to use only one switch. So that's this level 0 switch. So if you see that if your job runs on 48 nodes and it runs on some node with 0, 0 until 47, there's only one switch, and you should not see any. You should have the best latency and the best bandwidth for your application. If you need more than 48 nodes, you will end up with more switches, and then you will have up to 3 hops between 2 nodes. That's this level 1. That is up to 270 nodes. If your application needs more than 270 nodes, you will need the highest level of switches as well. That's this level 2. And then the application needs 5 hops at most to go up to 2 nodes. So then the latency is, of course, the highest, and the bandwidth could also be limited because there's not anymore the full bandwidth available at that level. So what you can control yourself is SBatch has an option minus switches, where you can say, I want at most 1 switch for my application. So that's only possible if your application uses 48 nodes or less. So here you can say, I would prefer to have just 1 switch, and I want to wait at most 1 hour to get that configuration. Another possibility is that you ask for, you use this constraint option, where you say, I just want my application to run on 1 of these cells, but not use more than 1. So that assures that there's at most 3 hops for your application. So if you know that your application is latency sensitive, then this is an interesting option. So the idea is it will run in 1 cell, but it can run in any of these. Okay. Then about the compilers and what is new.
Maybe we should state now what we don't tell here, because well, we don't talk about where the mount points are, where your homes are, where your work directories are, and which modules are around. This is not part of our talk here. We assume that all of you already used Mistral or have already used Mistral and know where to find their directories and how to use the module environment.
Yes. I know that Hendryk also has some slides about the module system still available. So if there's many questions about that.
As far as I saw, it's just about Spack.
But I think all the software is available there.
Yeah.
So everything that I'm talking about here is available in the Spack module system. So if you plan to not listen to the whole presentation, then this is probably the most important slide to remember about the compiler.
So first of all, you have to recompile.
You have to recompile, yes.
If you have an application ready at or had an application ready on Mistral, you have to recompile, because otherwise you will suffer performance penalty, because Intel compiler will not recognize the AMD CPUs as valid CPUs, and therefore just use basic x86 instructions and no vectorizations and nothing whatsoever. So please recompile.
Yes, so you might be lucky and get an error message saying, I do not support this CPU. Then you know for sure that you will need to recompile. Otherwise, it could be that indeed it uses instructions for CPUs from the last century, and you might not be using the system optimally. So yes, we were talking about what you should not do. So these are two important flags that you should not use, that I often see in configure or make files. Do not use this.
Because we recommended them for Mistral.
Might be one reason, yes. So do not use the -x flag for the Intel compiler. So do not use -x core AVX2 and do not use -x host. So if you're lucky, it only says, okay, you don't have an Intel CPU, you need to recompile. If you're unlucky, it will just run very slow. So what you should do is use this -m arch flag. Then you specify the architecture of the CPU, but you do not specify that it has to be Intel CPU. So what is the best here for the classic Intel compiler? So that's the Intel compiler that you have been using up to now. So that is ICC and iFort. The flag that you should be using there is -m arch is core AVX2. So the AMD CPU does not support AVX512. It only supports AVX2. So that's why we have this here. Now the newer compilers, so the newer compilers from Intel, but also the AMD optimized compiler, LLVM, and also newer versions of GCC. They also recognize this flag. -m arch is ZenVer3, so ZNVer3. So that is the Zen 3 architecture. So that's then again Milan. And it tries to, it will then generate code for the Milan CPU. You could also here use core AVX2, which is very similar, except for a few instructions that are extra on the Milan CPU. There's also the NVIDIA compiler, which also generates CPU code. It also generates GPU code, but for the CPU, you can also use this Zen 3 flag, and it also should optimize for the Milan CPU. Okay, that is the most important about the compiler flags, what you should be aware of to generate code that can actually be executed on the AMD CPU and is then optimal as well. Here I have some recommended application compiler flags for the applications that were also in the benchmark suite. I will not go through every single flag. You can look this up then later in the video or in the PDF that will be posted. Okay, I already talked about some of these. You will see the different versions that have been installed here on the system, and I think you need a module for all of these to get these versions. So there's the Intel compiler, which includes both the classic compiler, as you know, ICC and iFort, and it includes next generation compilers, which are based on LLVM, but optimized by Intel. There's the GNU compilers, which support all the languages and also support the Milan CPU version 11.2. There's AMD optimizing compilers, which is basically also LLVM, but optimized by AMD. And there is the NVIDIA HPC compiler, which is especially useful if you plan to use the NVIDIA GPUs. I will mostly focus on the Intel compilers in the next slides. Okay, so the Intel compiler, they have changed the name of the whole package. It's called OpenMP. Nowadays, it's mostly still the same package as was the Intel Parallel Suite for many years. So it still consists of the classic compilers, so ICC, ICPC, and iFort. But these compilers are not being developed anymore. So they will not get any faster anymore. They will not support newer CPUs, but they are still there because especially for Fortran, this is still the best, the compiler which gives you the best performance. They also have new compilers based on LLVM, which also include a new data parallel compiler. I will not talk about this, but this is also included in this Intel One API. It's based on SYCL. It's compatible with all the standards, as also already previous versions were. And the idea of the new compilers is that you can use it on accelerators, but the One API suite you can only use on of course, on Intel accelerators, so on the Intel GPUs, which are not yet available on Levante. So the new compilers, which are based on LLVM, the commands there are with an X at the end. So it's not ICC, but it's ICX, IFX, and there is also ICPX for the C++ compiler. So what Intel recommends is that for C and C++, it's already now usually faster to use the new compilers, so ICX and ICPX. That is already faster than the classic compilers. Intel at the moment still says that iFort, so the classical Fortran compiler, is still faster than IFX. But here it's interesting to test it out if you would like to have that little bit of extra performance. Also, the development of IFX goes quite fast, so it could there could be quite some changes between minor updates of one API. Okay, here is this. I said that there's quite big changes between minor updates of this new these new Intel compilers. What it supports now, it's everything up to Fortran 2008, except co-arrays, and some features of 2018 are implemented. For OpenMP, that should mostly work. OpenMP 4.5. There's also some offload, but that's only for Intel GPUs, so that's not very useful. There's a link here where it exactly says what features are supported and what not. Here I have a few slides with compiler flags. I will not go through them. Most important thing is that with the Intel compilers, you can use the same flags for the classic compiler, for the new compiler, as you were using for the classic compiler. So Intel has tried to translate the flags to this the next generation compiler versions. Only a few of the flags which were not translated, like this -MP1. And here is the same thing. This is for Fortran. It's also many of the flags were translated to the both compiler versions, to the new compiler version from the old one. Okay, I see there's a question. I cannot hear anything, but you can.
Sorry, I just wanted to comment on the fno math rno option. So your slide leaves it slightly unclear which one is the faster one, and fno math rno, unless I'm mistaken, is the one that improves speed.
Yes, yes. So the default, it's already optimal for performance. Only if your application actually checks rno, you will have to use this option. So by default, it's already optimal for performance. Only in case you check that, which actually I think almost no one checks rno after a math operation. So in pretty much any case, this is okay.
Well, just like floating point exceptions are not checked usually for Intel compilers.
Yes, but rno is still different from a floating point exception. So rno, this is, if you're programming Fortran, you can forget this. In C, you might want to check rno. If it does not ring a bell, then you do not have to worry about it. Is that, I hope that was clear. Okay, I'll assume that's yes. Here is again one flag which only works for the classical compiler, and Intel has not translated this to the new compilers. It's -FP trap. And that was what I wanted to say about the compiler. Then,
and that's where I jump in.
here, then they can hear you.
Yeah. So I'm Harald Braun. I think most of you already heard of me. I work for Atos already for like 5 years, so also already for Mistral and now for Levante. So, well, welcome back. And let's start with the recommended or necessary environment you need to run MPI or OpenMP applications. So for OpenMP, John already talked about how many threads you should use, and this number is 8 at max for hybrid code. So if you want to have a code that uses or exploits MPI and OpenMP and is good at it, you may use up to 8 threads, using 8 physical cores, using or sharing the same level 3 cache. And even if you are compiling with other compilers, you should consider using the Intel OpenMP library, since that one has, at least when it comes to the default, the ones that are, well, that perform the best. Well, if you're using Intel compilers anyway, just ignore this because you will use it. Sometimes, like for Icon, you may want to increase the stack size because sometimes applications tend to, well, allocate some arrays on stack, and the stack space on OpenMP threads is usually very limited to 33 megabytes, which may not be sufficient. If you need more, usually indicated by some segmentation fault, you may want to increase that. Usually for HPC applications, you may want to use KMP library turnaround, or the OpenMP standard environment variable would be OMP underscore. Oh my God, I forgot it. How long a thread spins until it joins. It's been a while. But
you mean OMP wait policy?
Yes, OMP wait policy. So for each of both, there is also a synonym, more or less, or similar environment variable giving the same result, more or less. So KMP library translates to OMP wait policy, and KMP affinity to OMP places, but OMP places has a different syntax. So usually you want to pin threads, and usually, at least all applications that I tried, you want to restrict all threads to only one of the SMT pairs, or one thread of the one SMT pair. Nonetheless, we keep SMT, or we kept SMT activated because maybe there are some kernel threads also. They may go there and find their free place. Yes, that was for OpenMP, and then to OpenMPI. We recommend to use OpenMPI because it supports Slurm and SRun and SBatch to the fullest. With Intel MPI, the placement support and so on is somewhat limited. So we recommend to use OpenMPI, and for OpenMPI, we recommend to use some kind of settings that mostly are already on the DKRZ info or documentation page. So, well, you can just read it. And usually you want to use UCX as well, underlying transport library. And this, of course, has also a set of or a bunch of possible settings. And well, these are the ones that we would recommend. The first one sets the kinds of transports you allow UCX to use. So in this case, loopback, so communication to itself via shared memory transports. And in this case, where what was the DC abbreviation again? Well, it's one protocol in IB. The other one that you may use for up to 128 nodes is the RC, which is reliably connected, but that one actually has a way larger memory footprint. So you may see problems when going or scaling up beyond 100 or 200 nodes. So therefore, it's recommended to use DC then. UCX unified mode tells the library that everyone or every participant in the set of processes sees the same kind of network and has the same kind of architecture, and therefore can disable heterogeneous supports. And last but not least, for large jobs, you may want to activate jobware adaptive routing, which is done using these two environment variables. If you like to see the full list of all runtime parameters, you can try the commands on the very bottom of this slide. That's it for OpenMPI. And then I'll move on to Intel MPI. For Intel MPI, there are actually two environment variables that are essential that you have to set in order to work well, get your application to fly with Slurm. First is that you specify that it should use PMI, in this case PMI2, and to point the library to the PMI library that manages the processes launched by SRun. Then you have to tell SRun to actually use the PMI2 interfaces. For performance, you should set the the variables on the bottom, which are that you tell the library which fabrics to use, in this case, shared memory and open fabrics. And for open fabrics, you may want to specify a provider. In this case, this is MLX, and MLX will translate to, well, UCX again. And therefore, you can also, well, use the very same settings from the slide before for UCX, like for Intel MPI, or to tune Intel MPI behavior. And of course, Intel MPI has also some kind of IMPI info, which can tell you a lot about the possible switches via environment that are there. But usually you don't need them. Okay, are there questions regarding the environment settings for the parallel libraries? If not, I would just proceed to, well, how to launch jobs on Levante. So first of all, I'll start off with, well, some pure OpenMP or serial job, because that's the, well, simplest thing to do. This looks, well, very much like on Mistral. I think one difference is that with the new Slurm version, there is no workdir or minus workdir argument anymore. This is now chdir, the directory to which as run or as batch or when starting a job should be open. Yeah, which is the working directory when starting the actual batch script. Okay. I think I don't have to tell more about this, because this is more or less the same like on Mistral. The more important or more interesting stuff happens once you start to use more than one node or to use MPI. And in this regard, we recommend to use SRun to launch your parallel applications in favor of MPI run or MPI exec, and I will only talk about SRun in the following. So stick to SRun. So what you see here is a command to launch pure MPI application, and what it does is, well, SRun is the command. L or -- label tells SRun to prefix every terminal and standard error output with the rank ID. The next one, -- hint no multi-thread, tells SRun to place processes only on the first SMT threads. With -- CPU bind -v, you tell it to actually report what the binding was. And then with -- tasks per node, in this case 128, you tell it how many tasks, well, there should be on a node. With minus minus distribution or minus m, you can tell it how to well, distribute or what the order of the ranks should be. In this case, it should do it using the policy block cyclic, which means block means it uses equally sized blocks over to assign tasks to nodes, and cyclic well, in a round robin fashion between NUMA nodes on a node. Actually, that cyclics works not that way as I said before. It assigns tasks to sockets instead of NUMA nodes. But that will be fixed. This is the fourth known issue that John mentioned. So, and if your application maybe is more memory bound and would not profit or even suffer from using too many tasks on a node, you may want to reduce the number of tasks, and this is then done by well, specifying that there should be only like 32 tasks per node, but every task will be assigned 4 CPUs or execution slots, and by that all tasks will be spread over the whole node to utilize all the memory bandwidth that is available, such that the 32 tasks do not sit all in the very same NUMA node, which would be possible. Okay. And this can be reused, of course, for, oops, where is here? For the hybrid MPI OpenMP applications. In that case, we just add an OpenMP num thread, in this case 4, which is the optimal number I found for icon. And well, in order to reduce again the number of tasks, to increase the available memory bandwidth per task or per thread, actually, you can reduce that in the same manner as explained before. So, well, that was the simple part. And then there are well, multiple ways to assign different things to different processes. Multi-program, multi-data. This is not new. So this was used, I think, for the MPE ESM1, where Eckham and what was the name of the ocean code again? The old one?
MPIOM.
Yes, were coupled via Oasis or something like that. And therefore you needed to have 2 applications or 2 different binaries in one MPI well, communicator. This is done in Slurm using some or via an NPMD configuration file, which specify which ranks should run which command. And there are certain or several ways to specify which ranks should run what. First of all, there is an asterisk. This asterisk takes every rank that is not specified otherwise, and the otherwise is that you either put list or comma separated lists of ranks or well, range of ranks there, and each line is per application. You can have, well, you can have as many lines as you have ranks, and well, I think the picture tells it all. And in order to actually use that, you have to put minus multiproc and path to your configuration file there on the srun command line instead of the actual application, because the application calls are already in that configuration file. This can also be used to actually run the very same application, but with a different environment. Likewise, if you want to have different OpenMP num threads for certain ranks or something like that. And there is none more. Oh. Proceed with the thing that is actually new with the newer Slurm version, which is heterogeneous jobs. And there are actually two kinds. First is the simplest part. It only has heterogeneous step within homogeneous allocation. So the allocation is done well, the very same way as before. But within the allocation, you can specify well, certain subgroups that should well, of ranks that should be assigned different well, resources or resource specifications. In this case, I put an example here on which the first 20 nodes should run 32 tasks per node with 4 CPUs each, and then the already known manner. But for the rest, I did not specify how many nodes here are, but the rest of the nodes will be filled with 8 tasks per node and with 16 CPUs each. So this may or may not be handy when doing actual NPMD, because this can also be, of course, be combined also, but has not to. But there is no need to. You can, well, call different applications in different heterogeneous, well, they call it groups. And in this case, the first group has 20 and the latter group, well, contains all the rest of the nodes. And well, then there is then the heterogeneous allocation, and this is the first time we actually touch the header of the S-batch. And here you can specify multiple different resource specifications separated by sharp S-batch head job delimiter. In this case, we request 2 nodes on partition compute. Well, just regular ones. For the second heterogeneous group, also 2, but we require them to have at least, we require them to have 12 gigabyte of memory. So large or a fat node. And well, there can be added even more of those heterogeneous groups in a job header. As many as you like. You can even combine different accounts, different partitions, different general resources like GPUs and so on. However, it makes it for Slurm not easier to schedule this kind of job. And it will look very much different from what it looked before on SQ, or if you look at it using scontrol, because actually you see as many jobs or submissions in the output of an SQ with the different head groups. And well, the launching of an application using those head groups, you can either specify those head groups as before on the header, and so in this case, in the uppercase, you can tell srun to run on the first 2, or only on the first 2, and then colon separated on another group. You may specify them in any order, well, as you like. It gives a lot of freedom, but well, there's one actual limitation. Head groups always consist of sets of nodes, which means you cannot mix on nodes. This has to be done differently, and well, this is then Elfenstaub. As already some of you know, if they did icon runs using my tweaks. Okay. And that's it for Slurm and how it should work. And who wants to go for the known issues?
Yes, let's. We share the burden, or?
Yeah.
Okay, so unfortunately there are still issues. I'm sure several of you have run into one or more of these. Well, we'll go through the ones that we know. The first one is a SIG bus error. and this occurs. You will see that applications fail with the SIG bus message while they are doing I/O on a Lustre file system. This problem was actually fixed with an update of the Lustre client on all the compute nodes. So this problem should not occur since the last 2 weeks. Should you still see these problems, then please report them, because at the moment we consider this problem closed.
And if you're already using some kind of workaround for it, you may, well, disable that to see if it's actually gone for you.
Yes. Okay. That's the SIG bus error. And then the problem which might cause most problems for your application, which is the endpoint timeout. And it might show up with these different error messages in your job. So it could either be error endpoint timeout, or you might see transport retry count exceeded. Well, the problem is that the InfiniBand cards in the nodes, in the compute nodes, they switch off for a short while, and then, well, then this node cannot communicate, cannot send messages or receive them, and then your application usually crashes. So the problem is that your whole job will crash, even though only one of the 900 nodes might have this problem. The problem is that the exact reason why the InfiniBand card switches off is not known yet. What we have done in the last weeks is to lower the frequency, and currently the turbo frequency on the CPUs is completely disabled. This was implemented to reduce the impact of this problem. What we see is that the performance impact can be around 10%.
But it's usually it's about 3%. What I saw on Icon, or
yeah, on average is less.
Yeah,
but it could vary from application to application. So we have disabled it to reduce the problem. What we see is that the number of applications, the number of jobs that fail with this endpoint timeout have decreased, but we also see that the problem still is still there, so that jobs still fail. So unfortunately, I don't have more news on this, but it is being investigated. What is exactly causing this? The permission denied on Lustre. I'm sorry that it's not yet in this presentation. I have here a few points. The problem here is that this is an error that only happens sporadically, as far as we know. So the problem is we do not have a reproducer for this problem, and that makes it difficult to debug and then find a solution for this problem. So what we have observed, what we know so far, is that it happens only sporadically, It seems to happen, especially for pool data.
In conjunction with ACLs.
Yes, EMAC and or Messi seems to be mainly impacted by this bug, and the use of ACLs could play a role in this problem. So I will put a slide with this text in the PDF, and then Hendryk can still post that online. So what you could do is inform the help desk if you can consistently reproduce the issue. That would be an excellent help to solve this. If you see that this problem occurs for data that is not in a pool, if it happens with any other applications besides EMAC and Messi, or if you see that the problem also happens without ACLs. If you see any of these things, if you see this error while you're not using any or all of these things, then please inform the help desk. That is so far the status of this known issue. And then the last one.
I think I already
you explained that this this flag does not use NUMA domains, but it is cyclic across the CPUs. I don't think it's fatal. Your application will still work fine. It's just not.
It's just a matter
optimal.
of well, a few percent of performance.
Yes. So this is I would guess a minor issue, but it will be fixed in a future Slurm version.
Well, and that's why we have this here, because this is the Elfenstaub from.
Yes. So this will be in the PDF, I think.
This is just as additional material on this slide.
Okay, so well, that was the presentation. Thanks for your attention. If you have any questions, then raise your virtual hand.
Yeah, I apologize that the colleague isn't there, so I have to do my very best to explain what he wants to explain you in more detail. It's about the spec, and I think it was John in the meantime, and also Harald, who mentioned that there is most of the software is based on modules, or is available via modules, what you know already from Mistral, that you do just a module avail or a module load to get your environment as you like it. But sometimes you run into problems with these, or you want to have more than just the modules available on the system. And that's why now on Levante, we use the Spack system. You might Google for it. It's a very well-known packet manager on HPC systems, very widely used. So lots of documentation out there, and it's really great. So for example, here is a problem. If you need to run or compile your code with netcdf Fortran, you can use the module load for a specific version of netcdf Fortran, but then you need also a long list of dependencies to compile your code, like MPI, HDF5, parallel netcdf, and so on and so forth. That's not shown. If you just do a module show on the netcdf module, you will not see all these dependencies. But you will see this magic hash, which is here K6XQ5G. That's the magic hash that Spack assigns to this installation of netcdf Fortran. And if you then query Spack find dp for dependencies on that magic hash, you will immediately see all the dependencies that you need to link to your program. So this is one of the good things about Spack. The other one, okay, here's an overview. So module system is very easy to use, but it often doesn't help so much in building your software. This is where Spack gives you much more information, and it also turns absolute paths into your binaries, which make them much more reliable than a kind of volatile module environment. This is also, it allows you to build your own software in user space completely. It's similar to Condor. And that means you can be kind of independent of the software tree, which might or not, may or not be good, but it might speed up your current transition to Levante once not all software is already installed. And for example, here, Ralph showed that what do you do if you want to install, for example, an older version of CDO, which we might not install as a module for everyone. Then please first refer to our documentation, because you can do it on your own. You can use Spack to query for the compilers that are available to build your software. And you can also check for packages that are available. So for example, yeah, just use Spack info CDO, and it will immediately tell you all the available CDO versions that you can build. And after selecting a version and the compiler which you want to use to build CDO, you can make a listing what dependencies will be installed also by using Spack-L CDO, and then the add version and the ampersand for the GCC compiler that you're using. And now the commands are really freaky, I would say. Once you figured out by the documentation, if you need an HDF5 or an MPI, or if you don't need an MPI especially, you can get rid of it. And by using these nice or even not so nice strings, you can then build your own software very easily and handle it independently of what we provide at the moment. So yeah, sorry for that very short presentation. If there is a need to go into details for Spack, either consult our documentation, or we might schedule another video conference for it. But this is really just to give you an impression that with Spack, you have much more power now than just with the pure modules.